Okay, in this first series of lectures, we're going to go over some first year notions. Let me explain what we're going to do. So the main idea is that in this course, we're going to rely a lot on material that you acquired in first year linear algebra in particular. And so I want to go over this material together. And also I am going to take the opportunity of this review session to introduce some notions that you might not have seen yet or that you have seen without really seeing. And the purpose of this is that I'm going to use some notation throughout the course and some ideas that I think are important, but that you might not have seen in the way we are going to see. And so I want everybody to speak the same language, essentially. So the purpose and the content of this lecture is as indicated here. I'm not going to spend some time detailing this. You'll have the slides anyway. By the way, before I proceed any further, let me point out that it is possible that the slides you will get are a bit more up to date than the slides I'm using here for my presentation. And the reason for this is if I find some typos, or if people point out typos, I will correct the slides, but I will not re-record this lecture. So if you see material that's a little different from these videos, what this means is that I have slightly updated the material. So the first thing I want to spend a little time on is something you have seen, but not really, I think, except if you've done 1240, I suppose. And so I just want to get these ideas in. And that concerns sets and logic. So let's begin with a set. So a set in mathematics is a collection of elements. And this can be any type of elements. I point out it can be functions, it can be matrices, it can be numbers. I mean, a set is a collection of elements. And we say that an element belongs to a set if it is in the set. And the way we denote this is using this notation that we are going to use throughout. This means X belongs to capital X, whereas this one with the barred slashed out belongs to means X does not belong to the set. Another important notion is that of subset. So a subset is simply a collection of elements that are in a given set. Just for curiosity's sake, I'll point out that we sometimes talk about proper subsets when we mean a subset that is not equal to the set itself. Okay, but that's not really important. Another thing that we are going to use all the time, and I just want to get down here, is quantifiers. So a quantifier is the most well-known ones are those two. For all x in X, this means for all elements X belonging to the set X, and this one, which means there exists an X in X. And as I indicate, these are quantifiers. The important notion also with sets is the intersection and the union, and this is something we will use from time to time. So the intersection of two sets is the set of elements that belong to both sets. So the intersection of capital X and capital Y is the set of X that belong, little x, that belong both to capital X and to capital Y. whereas the union of two sets is the set of elements that belong to one or the other of the sets. And I will mention, make it very clear that in mathematics, when we talk about OR, we mean and or in common parlance. Okay, so what we mean when I say the union, little x belongs to x or it belongs to y, it can be in x, it can be in y, or it can be in the intersection of x and y. Okay. The other thing that I want to spend a little time on is very basic logic. So, because this is something we'll use throughout, and this is something you have seen, but I think it's important to sort of put it down formally. So, and then, let me point out, this is not very formal, but okay. So, in a logical sense, proposition, what we call a proposition, is an assertion or a statement whose truth value, whether it's true or false, can be asserted. A theorem is a proposition that we have shown to be true. The sky is blue would also be a proposition, but it's something that's going to be difficult to prove. Okay? Now, if A is a proposition, we typically write A to mean that A is true, and not A to mean that A is not true. Okay? And if you want that the contraposite of A is true. Now, if we have two propositions, we write A implies B to mean that whenever A is true, B is also true. And we write A equivalent to B, which we also say A if and only if B. And that means that both A implies B and B implies A are true. Okay? We say they're equivalent. And one very important property that is used many, many times when proving things in mathematics is that A implies B is equivalent to not A implies not B. And it is very likely that you have seen proofs that have used this in the past. Another important notion in logic, and that you'll see used from time to time, is that of necessary or and sufficient conditions. So suppose we have a statement P, which we want to determine whether it's true, and we want to determine this depending on the value of another statement, H. Well, we say that H is a necessary condition if P implies H. Okay. So in words, this means it's necessary for H to be true, for P to be true. When P is true, or H is always true. What we call a sufficient condition, that's the opposite, when H implies P. Okay, so in that case, what this means is it suffices for H to be true, for P to be also true. And finally, we say that H is a necessary and sufficient condition if H is equivalent to P. The last thing I want to go over in terms of logic and quantifiers is the fact that you can play logic games with quantifiers. So what happens is that the quantifier for all and there exists are linked in the following way. There exists is the contraposite of for all. So if you have a statement, and this you might have seen in first year calculus, for example, because this is something that comes up when you define continuity or limit. So the idea is, if I say for all x in x, there is a y in y, and I take the contraposite of this expression, so the negation of this expression, if you want, that contraposite is there exists an x in x such that for all y. So you're switching one for the other. So the second notion I want to go over is complex numbers. So this you may or may not have seen. So I know, for instance, in 1210, if you've taken 1210, then you have seen complex numbers, whereas if you've taken 1300, you have not officially seen them. You might have seen them in other lecture courses, and again, this is the reason why I'm going there. So complex numbers are very interesting constructions, and they come into play very, very often, and we will be using them many times. So that's why I want to go over them. So a complex number is a very simple thing. It's something that's defined in the following way. You take an ordered pair, A, B, of real numbers, and what you do is you write A plus IB or A plus BI, where you take I to be the number, so to speak, such that its square is equal to -1, or I is the square root of -1. Okay, so in what you've seen before, this doesn't make any sense. Square roots have to be of positive or non-negative real numbers. But here we're defining this I to be the square root of -1. Okay? And the set of all complex numbers we then denote C. Okay, so C is the set of all AB such that A plus IB. Now, this is an arbitrary construction, but it plays a very, very important role in an extremely varied number of cases. So just admit that this is the way we define these, and given this, we can study the properties of numbers that are defined this way. So in terms of adding and subtracting or multiplying complex numbers, so suppose I have two numbers, A plus IB and C plus ID. The addition is simply the sum of the elements that don't have an I in front and those that have an I. So you see that A plus IB, which is a complex number, and C plus ID, the sum is A plus C plus I times B plus D. And the multiplication works a bit the same way. It looks complicated, but it's very easy to do this computation by hand if you realize that once, when you take that double product, IB times ID is I squared BD, and I squared is equal to -1. Okay? And there's nothing very important here. It's easy. The part without the I we call the real part of a complex number, and the part that has an I in front is called the imaginary part. Okay. The properties of complex numbers. So suppose I take three complex numbers, alpha, beta, gamma, then summing and multiplying, both are commutative. That means alpha plus beta is equal to beta plus alpha, and alpha beta is equal to beta alpha. There's associativity, which simply means that you can take the sum of the products in any which way you want. There's a 1 and a 0. And so if you add a 0 to any complex number, you still have the same number. And if you multiply a complex number by 1, you have the same number. Now, given a complex number alpha, there is a unique complex number beta that is such that alpha plus beta equals 0. Okay, so that's what we call an additive inverse. And there's a multiplicative inverse the same way. So for any alpha non-zero, there is a unique beta in C such that the product is equal to 1. And finally, multiplication of complex numbers is distributive over addition. That means gamma times alpha plus beta is equal to gamma alpha plus gamma beta. And I'll point out in the first assignment, I'll have a few exercises for you to play with, and in the tutorials, you might go over some of those notions. These are very easy properties to check, okay? Provided you use the definition here of complex numbers and the addition and multiplication, as we have seen here, those properties are super easy to check. I've talked about additive inverse and multiplication, etc. So here are some examples. So if I take alpha and beta, remember I said there's a unique, for every alpha there's a unique beta such that alpha plus beta equals 0. Well, if alpha is the number, then minus alpha is the additive inverse, okay? So alpha plus minus alpha is equal to 0. Subtraction is simply obtained by adding minus a number to the other. The multiplicative inverse is obtained here, and division is simply multiplying by the multiplicative inverse. As I said a little earlier, so if I write a number as z equals a plus ib, what we call the real part of z is the a, and the imaginary part of z is the b, so the number that is prefixed by I. Now, two very important quantities are the conjugate, the complex conjugate, and the modulus. So the complex conjugate of a number, z equals a plus ib, is z with a bar on top, and it's simply a minus ib. Okay, so instead of b, you use minus b. And the modulus, and sometimes it's called absolute value, but I will always say modulus. The modulus of z is the square root of the sum of the squares of the components of z, okay? And that is always a non-negative number, real non-negative number. So some properties of complex numbers are listed here. I suggest you take a look. What's important here, probably one of the most important one is this one here that you see. It's that the conjugate of the conjugate is equal to the number itself. This one here is very useful. It is that the product of a number and its conjugate is the square of the modulus. And all these other properties are quite important. I suggest you take a look. One that is very, very useful is this one, the triangle inequality. So the modulus of a sum is less than or equal to the sum of the moduli. Now, let me point out the main reason why complex numbers are so important. And for this, I'm going to come back to something that you've probably seen in high school, which is solving quadratic equations. So suppose I look at this polynomial, p of x equals to a0 plus a1x plus a2x squared, where x, a, and the a's are all real numbers. So this is a second degree polynomial, and you have seen probably, I hope you have seen, and if you have not, it's important to know this, that what you do is define this delta, which is sometimes called the discriminant, which is a1 squared minus 4 times a0, a2. And what you know from past life probably is that if delta is positive, then the p of x, the equation p of x equals 0, has two distinct real solutions. x1 equals to minus a1 minus square root delta over 2a, and x2 equals minus a1 plus square root delta over 2a. And if delta equals 0, then there is a real solution that has, it's called multiplicity 2. So it's actually, if you take the equation above here, you can see that if delta is 0, both x1 and x2 are equal. Okay, and what that means is, in that case, we have a unique real solution. And what you saw when you did this in high school is that if delta is negative, there is no solution to p of x equals 0 when p of x is equal to this. Okay, so if that discriminant, that delta here, is less than 0, there's no solution. So that's when you're looking for real solutions. But now let's suppose I'm looking for complex solutions. So what happens now? So I consider the same polynomial, and I'm still assuming that x, a0, a1, and a2 are in R. Okay, they're real numbers. Now, instead of seeking an x in R that satisfies this solution, let me seek an x in C, so a complex number. So here things are the same, but when delta is negative, what changes is that I can do the manipulation that is written here. Okay, what you see here. Square root of delta, remember delta, suppose delta is negative. Square root of delta in that case is square root of minus 1 times minus delta. And square root of a product is equal to the product of the square roots, and so I have square root of minus 1 times square root of minus delta. Minus delta is negative, so minus delta is positive, so that square root is well defined, and square root of minus 1, as we've seen before, is I. Okay, so in the case where delta is negative, minus delta is positive, the square root is usual, and we can proceed as normal. Okay, so let's consider the problem again. So we have our polynomial, we have our coefficients and x in R, and now we're looking, on the other hand, for a solution x that is not necessarily in R. So we compute the discriminant, delta equals a1 squared minus 4a0 a2, and we say p of x equals 0 has two solutions. x12 equals minus a1 plus or minus square root delta over 2a, where if delta is negative, x1 and x2 are complex, and they take the form of minus a1 plus or minus I times square root of minus delta. So you see how allowing delta to be negative and using the imaginary I allows us to find two solutions. And why is this important? Well, we'll come back to eigenvalues later, because this is something you have seen in first year linear algebra. But okay, let's take a very brief review here. So we have a matrix A with entries A11, A12, A21, A22. Okay, and when we look for eigenvalues of this matrix, what we're doing is we're seeking values lambda that are solutions to determinant of A minus lambda times the identity matrix equals 0. So that is lambdas that are solutions to this equation here. Okay, so A minus lambda I is simply, recall, and we'll come back to that identity is simply the matrix with 1s on the diagonal and 0s everywhere else. So A minus lambda I is this matrix A11 minus lambda, A12, A21, A22 minus lambda. I take the determinant of this, and I remind you that the determinant is simply the product of the diagonal entries minus the off-diagonal entries. So that's what the determinant is here. So I'm looking for solutions. I expand this term here, and I find lambda squared minus those a11 plus a22 lambda plus this. And I'm looking for solutions to this. Now, what I do is what we did before. This is a second degree polynomial in lambda. Okay, lambda is the unknown. I compute my discriminant delta, which is simply the square of this minus 4 times the product of the other terms. So this is this number here, and in the end we get this. So the discriminant is a11 minus a22 squared plus this number. Now, a11 minus a22 squared is, of course, a non-negative number, but this could very well, this term here could very well be negative, so it's possible that delta will be negative. But using the method I showed before, if delta is negative, then I take I times square root of minus delta. And so here we see that allowing solutions to be complex, we find two potentially equal, okay, that's if delta is equal to 0, solutions x12 equals a11 plus a22 plus or minus square root delta over 2, where square root delta might be I times square root of minus delta if delta is negative. And I suggest that you take a look at this example here. For example, compute the eigenvalues of this matrix, and you will see that they should come out to be complex. And that's it for complex numbers. Okay, something else that I want to go over are vectors and vector spaces. So vector spaces you might not have seen entirely in your first year algebra class, but you have seen the notions, and I'm just going to give a few more definitions. So the first thing is a vector. So a vector, and we'll call the one here A, is an ordered n-tuple of real or complex numbers. So an n-tuple is simply n entries, okay? And here and later, what I'm going to do is I'm going to use that capital F with 2 bars to denote either R, the set of real numbers, or C, the set of complex numbers. Okay, so if it's not really important whether we are talking about real or complex numbers, I'll just use the notation F. Otherwise, I'll make it clear that we're using either R or C. And so for numbers A1 to AN in F, we denote A equals this n tuple, and we say it belongs to F to the power n. So that would be R to the power n or C to the power n. And this is what we call a vector. The A1 to AN are the components of A. Typically, you will see often when we're writing things down, we'll just write an A. Otherwise, if possible, we could use a bold A or an A with an arrow on top. In this course, as much as possible, I'll try to use bold letters for vectors. Okay. Now, this is something you might not have seen, but it will make a lot of sense if you think about it. So this is what we call a vector space. A vector space, and we say over F, so over, it's called a field of numbers, but it doesn't really matter. So a vector space over F is a set V that's equipped with two binary operations. One is called vector addition, and typically we denote it plus, and the other one is scalar multiplication, which is typically denoted either with a dot, a small dot, or with nothing. And for V to be a vector space, elements in V, together with these two operations, they need to satisfy those 8 properties that you see here. So the first property is, we saw it before, it simply says that when you're adding, the order in which you add doesn't really matter, okay? So this is, I can add the result of V plus W to U. It's the same as adding U and V and then adding W to this. The second property simply says that addition is commutative, okay? It doesn't matter which way you do it. The third says that there is a zero vector, which is such that if you add it to any other vector, that other vector remains the same. There's also an inverse element. Then if you take a real, and actually you could take also a alpha in C, it would work also, but the fifth property here I've written with R. As again, it could be for all alpha in F. So for any two vectors, if you multiply by the scalar alpha, it's the same thing as multiplying each vector by the scalar alpha and then adding. If you take two scalars and you add them and you multiply by a vector, it's the same thing as multiplying the vector first by the scalar alpha and then by the scalar beta. Finally, it doesn't matter if you're first multiplying by a scalar and then a vector, or multiplying the two scalars together and then multiplying by the vector. And the last one is that there exists also a neutral element for multiplication, and that is 1. So for all vectors V in the vector space, when I multiply the vector by 1, by the number 1, I still have the vector. Okay, so this is the formal definition of a vector space, and actually all that you have seen in first year algebra falls under the vector space category, although you might not have seen it called that way. And we're not going to spend some time proving that things are vector spaces and so on. This is something you will do in other math courses. But just be aware that this is like a framework within which we are operating. Something else that is important with vectors is the notion of norm. And this is something that will come back at some places in our course. Okay, so if I have a vector space over F and I take a vector V in this vector space, then the norm of V, which we denote with these two double bars, is a function from V to the set of non-negative real numbers, and it has, that function has the following property. It's non-negative. Okay, that's the first property here. For any vector V, the norm is a non-negative function, and it's equal to 0 if and only if the vector itself is 0. The second property is that when you multiply a vector by a scalar, alpha V, the norm of this multiplication is the modulus or the absolute value, depending on whether alpha is in C or in R, times the norm of the vector. And lastly, this is something we already saw with complex numbers, if you remember. If I take any two vectors in V and I compute the norm, the norm of their sum, that norm is less than or equal to the sum of the norms. Okay, and this is what is called the triangle inequality. So norms are very useful. One norm that you probably have seen already, and that we'll talk about in a minute, is the Euclidean norm, which is essentially the distance or the length of a vector. Now, to exhibit a few particular vectors, so let's call Vn, just for the size, let's call Vn a vector space and say it's R3 or R2. Then we call the zero element or zero vector. This is simply the vector composed only of zeros. Okay. The additive inverse of a vector A is minus A, which has the components of A with a minus sign. And you can see that if you add A and minus A, entry by entry in the vector, component by component, you're going to get A1 minus A1, A2 minus A2, and so on and so forth until an minus an, and so you'll get the zero vector. So that's indeed how the additive inverse is defined. The Euclidean norm, which is the length of a vector, this is simply the scalar square root of the sum of the squares of the components of the vector. Okay. And another thing that we'll use from time to time, or you'll hear me mention from time to time, is the normalization of a vector. So if I have a vector A, I will call the normalized version of A is simply this A tilde, which is the components of A, so A divided by the norm of A. So remember that norm of A is a number. I'm not allowed to divide a vector by another, but here I'm multiplying the vector A by 1 over the norm of A. So this is a allowed operation, and that vector, you can very easily check that it has unit length. So if you compute the norm of A tilde here, you will get some 1. Okay. So this is a vector that has the same direction as the original vector, except that its length is 1. And this is very useful. We often want to talk about a vector that has unit length. Finally, something that will come up from time to time is what I'll call the standard basis vectors. So here I'm starting with R3, so a three-dimensional vector space of real numbers. So there we typically denote I, J, and K, what we call the standard basis vectors. Okay, this is 1, 0, 0, 0, 1, 0, 0, 0, 1. And what's important with those vectors is that we can write any other vector, like the one that I have here, A equals to A1, A2, A3, I can write it as the sum of the components of A times those standard basis vectors, okay? And this is very important. This is why we use those vectors. And finally, in Rn, so if instead of considering R3 as we were doing before, in Rn, the standard basis vectors, we typically denote them E1 to En, and for a given value of k, Ek would be the vector that has k minus 1 zeros before, then a 1, and then n minus k plus 1 zeros again. So the 1 would be in the kth position in this vector, and all the other numbers would be 0. And that's all for now for vectors. Okay, continuing with vectors, let us now take a quick look at the dot product. So I remind you that the dot product is defined in the way that is written here. So if I have two vectors A and B with components A1 to AN and B1 to Bn, then the dot product is a scalar, okay, so it's a value in R that is simply defined as the sum of the entry-wise products of the vector elements. So it's a special type of inner product which you might see later. Now, in terms of the properties of the dot product, we're going to go over just a few. So here, note that I'm working in Rn, not Cn. So I'm specifying that I'm working on a real space. So the dot product of a vector with itself is the square of the norm. So that gives an interesting relationship between the product of a vector and its length. And this means in particular that when you take the dot product of a vector with itself, you have a number that is a non-negative quantity. The dot product is commutative. That means there's no difference computing it in the direction A and B or B and A. It's distributive over addition. It's also, it doesn't really matter what way you multiply by scalars. And the dot product of any vector with the zero vector is the number, the scalar 0. Now, why is the dot product important and interesting? It's because it gives a geometric interpretation of some quantities. So in particular, if you take a look here, so if I have a dot product of two vectors, it is related to the product of the length of these vectors, so the norms, times the angle between those vectors. So an angle, of course, in Rn is difficult to visualize, but think about something in the plane or in free space, and it's easy to see what this is talking about. Okay, there's a very well-known inequality that is associated to the dot product, which is the Cauchy-Schwarz inequality, and it simply says that the absolute value of the dot product is less than or equal to the product of the norms of the vectors. And one of the main reasons why the dot product is so important is that last theorem here, which says that two vectors are orthogonal if and only if their dot product is 0. So that is a very good way of characterizing two orthogonal vectors. One thing that dot products come in handy for is in terms of scalar and vector projections. Sorry. And so here you have the way to compute the component of a vector along a certain vector and the projection, the orthogonal projection onto another vector. Okay.